Okay, so I'd like to thank the organizers, and this is working much better than I thought it would, so I'm impressed. So I was told to give an overview of cosmology and how we might use cosmology to discover new physics, so I'll give it a shot. So the audio is okay, right?
It's good, yeah.
Okay, thank you. Let me just start by reviewing the fact that inflation is a very successful theory thus far. So this plot is the famous CMB observational plot, but it teaches us a lot already. So we know that the universe is homogeneous and isotropic. The data points on this plot, of course, the error bars are quite impressive. But inflation not only predicts a flat universe that's homogeneous and isotropic, but it also gives us a spectrum of Gaussian, adiabatic, and nearly scale invariant fluctuations. And it also provides a mechanism that generates super horizon fluctuations in a causal way to explain the temperature differences we see in the CMB. So that said, the typical models of inflation that you might have predicted, we can rule them out. So simple power laws, you can see in this plot here, powers of the field you would have expected. Those are highly constrained by the observations of the CMB. And in particular, what's really exciting is this ratio of the tensor to scalar ratio, or in other words, primordial gravitational waves, which we parameterize by this variable r, versus the amount of scale invariance, which is determined by this parameter ns. And I think everybody's probably seen this plot before, but what's interesting is this original Starobinsky r-squared inflation model seems to be very convincing versus what we would have thought maybe from just naive quantum field theory. These models seem to be ruled out. And in addition to that, we have the interactions of the inflaton, whether it's with itself or with other fields, characterized by this FNL parameter. And it seems like there's little or no interactions that are present according to the current data. So for example, self-interactions seem to be ruled out. Any particle production or other things seem to be ruled out. So it just seems like that inflation took place, and it might have been very simple. And again, this Starobinsky model, and I'll say more about this in a minute, really seems to be favored by the data. So you might say this is a maximally boring universe in the sense that you have inflation and nothing else. And these measurements will improve. So in particular with CMB S4 and other experiments coming up, we'll really tighten the window on what will be seen. So again, this axis is the level of gravitational waves in the Earth, primordial gravitational waves, complementary to what we just heard about, versus the tilt of this power spectrum. And this is the estimate of what CMB-S4 will see in the future. There's stage 3, which is this purple region. And really a benchmark in this is this 0.003, because again, these models that seem right now really in favor, for example, R-squared or Higgs inflation, those will be able to be ruled out, or potentially ruled out with future observations. And by future, given the current situation, I don't know what future means, but near-term experiment, we'll be able to address, to rule out these things. On the other hand, if we actually detect primordial gravitational waves, one important thing is that we will be able to determine the scale that inflation took place at. So down here, I have the scale of inflation versus the Planck scale. And if you measure some value of R, this would tell you the scale that inflation took place at, which would require some new physics. And so that would tell us the scale of new physics. And here on the right, although, so this parameter M is parametrizing the potential in terms of the inflaton divided by some scale of new physics. And so depending on how far the field moves during inflation, you have, these different lines that appear in the plot. So this is an experiment that is going to take place. It's currently being developed, and these are the constraints that we've placed on it. In addition to that, we also have the bounds on ineffective. So the light degrees of freedom that are present in the early universe. So this plot is showing the projection that CMBS4 will see. I don't know how to get rid of this window, but that's okay. So on this side, we have the change from the standard model degrees of freedom. So the current limit at 2 sigma is this dotted line across the top. And depending on the spin of the particles, you have the blue line, the green line, and the purple line. And this temperature at the bottom is the temperature at which these degrees of freedom, presumably beyond the standard model particles, decoupled from the standard model. So that's the temperature on the bottom line. So with CMBS4 or something similar, this is the bound that we'll place on the number of change in the degrees of freedom. So if you have new light particles in your favorite particle physics model, these are the constraints that the new experiment will put on the presence of these particles in the future. Okay, so let me pause there for a second. Okay, so that's sort of the standard. I could also talk about neutrinos. The sum of the neutrino masses during CMB decoupling will also be important. But I figure that, especially in the parallel sessions, people will talk about this stuff. So I wanted to try to talk about some stuff that I don't think is as popular. And in particular, what I mean is connecting the end of inflation with the time of Big Bang nucleosynthesis. So, of course, we know at BBN that the universe was radiation dominated, but how you connect inflation with BBN, and in particular, how do you reheat standard model degrees of freedom, that's not so clear. And we've had a couple of workshops recently at Aspen and at KITP, and trying to understand this region in the middle it's not only interesting for trying to explain the actual universe we live in, but of course, that's where LHC physics occurs as well. And so that's what I wanted to focus on in the rest of this talk. Okay, so I took this out of a textbook. If you go to your textbook and you look up what's inflation, we all know inflation took place. You have some period of slow roll inflation. The end of inflation is when the field rolls down into its minimum. It oscillates back and forth, and then it's supposed to decay to the standard model. It reheats, and we have a thermal universe that we live in, and that's what we call the hot Big Bang. That process is actually very complicated, which some people have known for a while, but I don't think this is that popular. So when you have those oscillations, they can be highly nonlinear. You can have a period of non-perturbative parametric resonance. What does that mean? It means that, for example, let's say the particles you're decaying into are bosons. You can have a condensate that forms. If they're bosons, you have the statistics that are important. So there can be a collective channel, so the energy goes in quicker than you might have expected. So that's what we call parametric resonance. the decay process can be nonlinear. You can have chaos, you can have turbulence, and in particular, you can form clumps, which I've tried to show in this picture here. And these clumps, and even infiltrons that don't decay completely, these clumps could take a long time to decay. And depending on the nature of this and how long it takes them to decay, this is going to affect the evolution of the universe. And I'm stealing this from my friend Mustafa Aman. This process requires some serious simulations to understand. And then on the other hand, you can ask, how long does this actually take? So we said that we know from observations that the infiltron seems to not want to couple to other fields very strongly. So you can imagine that this process might take a long time. And if it takes a long time, how does that affect the evolution of the universe? So in other words, when we're looking at the end of inflation, and then we're thinking of the time of Big Bang nucleosynthesis, what is the equation of state in between? And for example, let's say you still like WIMPs, they're going to be produced in a phase where the equation of state is not radiation dominated, and so that in principle throws off what you would expect, for example, the cross sections and other predictions. So in other words, if you think of sort of the textbook example is you have the end of inflation. Inflation immediately leads to a thermal bath of particles, and then you just have the regular evolution. Instead, you can have something where inflation, either the process of the decay of the infiltron is long-lived and it leads to some matter domination or some other phase, or you have other particles and it leads to some other phase. And so we really need to compare the two possible histories as opposed to just assuming that you have instant reheating. Okay, so all that said, one criticism would be everything I've really said, the constraints on inflation, the amount of interactions, the level of non-Gaussianity is really being measured around 50, 60 e-folds before the end of inflation. And that's where these constraints are coming from. Whereas, at the end of inflation, you could say that anything goes. The potential can change. Why can't I just add some dimension 5 or dimension 6 operator that allows the field to decay, or something else that occurs completely different? Because the constraints we have observationally are really around the window at the beginning of this. And the point I want to emphasize about that is, first of all, if you want to understand whether inflation takes place or not, you need to calculate corrections to this potential. And to calculate those corrections, you need a UV complete theory that allows you to calculate those corrections. And why is that so? Because we know that gravity is non-renormalizable. And in particular, if you just write down your favorite infiltron potential, let's pretend for a minute that this is still a viable potential, but you can write whichever one you like. We believe that there are new degrees of freedom at the Planck scale. And from an effective field theory point of view, one way to parameterize those is just to write down some parameterization like that. So some tower of states and powers of the potential. Or if you don't like that, just the idea is we're parameterizing our ignorance of whatever happens at the Planck scale in terms of some Taylor expansion. But we know that those new degrees of freedom need to be present. And even at the level of a dimension 6 operator, this leads to what's called the eta problem, meaning that these corrections will lead to a Hubble scale mass for the infiltron, unless there's some mechanism to suppress that. Okay, so if that was complicated, the main message I'm saying is there's new physics at the Planck scale. Inflation is close to the Planck scale. Unlike, for example, the Higgs potential, you don't need to worry about Planck scale, although somebody might contradict me in this conference, but you don't need to worry about Planck scale corrections to the Higgs potential. But in the case of inflation, the inflaton is close to the Planck scale, and these corrections are really important. So you need a theory that you can calculate these corrections. And the only theory I know of you can actually do that is called string theory. And so the main point that I'm trying to make right now is you can't just have the inflaton. You need a bunch of other stuff that comes along with it. And if you're having a UV complete theory of inflation. So in particular, you end up with a picture like this. And the generic prediction is that, let's say you have inflation taking place over here, and then you have the standard model sitting over here, and then you have, you know, some hidden sectors, your dark matter sitting over here. There are two generic predictions you expect. You expect other fields besides the inflaton. Let's call those moduli. And you expect that there'll be many sectors, not just the standard model that you would want to reheat to. So you isolate, let's say, the inflaton in some region, but you have the standard model in some other region, and then you have a bunch of other sectors. And the question is, why would the inflaton prefer the standard model over all these other hidden sectors? So that's one challenge that I think hasn't really been addressed. And in the presence of those other fields, they also oscillate. So even if you don't have prolonged reheating, which I was motivating earlier, you can have these other fields that oscillate, and they also would change the equation of state prior to Big Bang nucleosynthesis. So the way the universe is evolving between inflation and standard model physics is unknown. And again, it's in the region where particle phenomenology is interesting. And again, these things are well motivated. They have experimental predictions. They change the way that we match our CMB predictions for inflation. They change the way that WIMPs would behave, recombination. And then on the other hand, theoretically, I hope I've already motivated how this works. So moving on, the main thing that I'm trying to emphasize right now is when you have the simple picture that inflation gives rise to these oscillations at the end, and it decays into standard model particles. Why the standard model? Why not one of these other hidden sectors? And how many other hidden sectors are there? And why is it preferred? And I think that's interesting. There's been very little work on this, but it's sort of an old story. Move this. So Lev Kaufman with Yi a long time ago pointed out this is sort of a cartoon of how UV complete theory of inflation might work. This is one of the simple ones. So you have two D branes, they're trying to collide with each other. Once that happens, they produce these closed string loops. That leads to KK modes and gravitons, but then those need to go to the standard model sector. And you can imagine there are many standard model sectors. Some are hidden and some are not. And this picture obviously is quite complicated. And this has not really been worked out in detail. There's a couple notable papers where people actually did this from a top-down point of view. And again, I want to emphasize the top-down point of view is important because that's where you can calculate the corrections to the inflationary model. And for example, these two works, when they actually worked out a UV complete model of inflation and then tried to show how you get reheating, you find out that the standard model, this is the branching ratio versus the decay to the hidden sector, you can see it's much less than 1. So it seems like there's a problem trying to get the energy from the inflaton into the standard model. Okay, so this is PHENO. So I didn't want to talk too much about string theory because you don't want me to. So let me switch over and try to give a phenomenological model that might realize some of these things that I'm trying to motivate here. So in particular, again, it's these hidden sectors versus standard model degrees of freedom. Okay, so in particular, let me focus on this model of co-decay, which was introduced by these authors. some time ago, but it has the general characteristics that I'm trying to motivate here. So the idea is that early on, the dark sector decouples from the standard model, and even while it's relativistic. So imagine you have the infiltron, it decays into all this stuff, and this dark sector decouples from the standard model while it's relativistic. Okay, so then you have two sectors. You have the standard model sector and the dark sector. Again, you probably have more than one dark sector, but let's say you only have one. So in the dark sector, you can actually keep, there's going to be two different temperatures, the temperature of the dark sector and the temperature of the standard model. And inside the dark sector, let's say you have two particles, A and B, and they're scattering with each other, allows them to maintain equilibrium in their own sector. And so that's this A, B scattering. And then at some point, you can have these light particles that decay into the standard model. Let's call those the B particles, whereas A cannot decay. And then eventually this dark matter freezes out, and these A particles, which can't decay to the standard model, become the dark matter. I don't know how to kill this window, but okay, there. So the key point is the dark sector is not in thermal equilibrium with the standard model, but it's in equilibrium with itself. So the temperatures scale differently, and the dark sector particles are in equilibrium, and there's no Boltzmann suppression. So let me try to illustrate that with the standard plot everybody's seen. So this is the co-moving density on this axis, and this is time, or mass divided by temperature. So usually, right, everything's in equilibrium, and then it would decay exponentially through the Boltzmann suppression. But because of this equilibrium in the dark sector, this thing actually maintains its distribution until the time of B decays, which happens at this point here for this particular choice. So then they decay, but as they're decaying, that means the A particles and B particles become separated, and then the A freezes out, and that gives you the abundance of A particles. Whereas the B decays all the way down to the standard model. You might wonder, why is the A decaying? But that's because the B and A can't scatter like they were, and so that suppresses the A abundance. Okay, so if this seems like nonsense, let me give you a concrete example. Let's just say you have a dark version of SU2 electroweak theory. So this is just like electroweak, but now it's on the dark side. And so you have some dark Higgs, it gets some Bev. The fact that you have the custodial symmetry is in the standard model, that means the masses of the would-be dark Z and dark W are roughly the same. You can break this through some higher dimensional operator suppressed by some cutoff. And so you have the stable dark matter sector would be this W, whereas the decaying particle would be the Z. And that would decay to the standard model. So just as a quick example of how that might work. So one thing this realizes is the idea that in particular, besides the fact that you have two sectors that are separated, if you study these models for different choices of parameters, and I'm trying to go fast on time here, but if you look at the parameter space, obviously there's constraints, for example, from indirect detection of dark matter. If you put all those constraints in, you have a region of parameter space where this model would start with a radiation phase, but this dark sector would take over the energy density of the universe. It would become matter dominated. And then once it decays, you get back Big Bang nucleosynthesis. So again, the message is you get an early matter dominated phase in that gap between the end of inflation and BBN. So the reason that's interesting, especially in this case, is if those particles decouple early from the standard model, then if you have a matter phase, you can develop structures in the early universe because cosmological perturbations grow during a matter phase. So you'd form clusters of sort of dark clumps or you could call them ultra compact mini halos. And those things, if they survive to the present day, would actually give rise to boosted factors for detecting dark matter collisions in the late universe. Whereas earlier studies, especially by Erichek and Sigurdsson, and also a paper we wrote with Gigi Fan and my student Ogun Ozoy, you usually don't have that effect because dark matter will stream out. Free streaming effects would destroy such signals. But because this decouples early, which I've tried to motivate is generic from the UV point of view, then you would actually detect this stuff. Okay, so in summary of this bit, the point is that if you have such a setup where you have this hidden sector and it's strongly decoupled from the standard model, meaning gravitationally coupled, then it could lead to these enhanced effects. Here I'm quickly plotting this. And these substructures that could form in the early universe. So you have matter domination before the typical matter domination. Maybe that leads to some interesting signals. Maybe not. Okay, so how am I on time? Yeah, okay.
You have about 3 minutes.
All right, I'm wrapping it up. Everybody wants virtual lunch, I'm sure. All right, so the other thing that's interesting about matter domination is if you have these structures forming, you could ask, can they collapse to actually form black holes? And we heard in the last talk, there's this interesting mass range of about 30 or in between, between let's say 20 and 100 solar masses for black holes. And let me make this kind of short. The point is, if you have this matter phase, whether it's from infiltron not decaying fast enough, these moduli fields or additional fields that are driving the energy density, during this time, you can form black holes. And usually when you look at primordial black hole formation, the probability, this beta, that they would form is usually based on an argument that you need a mode that comes into the Hubble radius that's strong enough to collapse and form a black hole because you have Jeans pressure pushing out, and there's a competition between the pressure term right here versus the expansion collapse. And essentially you need a mode that's just large and collapses and forms a black hole. But what's interesting in a matter phase, which was first pointed out by Zeldovich and Klopov and collaborators, is that in a matter phase, these things can grow over time because you don't have the Jeans pressure to prevent them from collapse. So I don't have much time to discuss this, but what's kind of curious about this is, so what's the, if you have this matter phase, whether it's from co-decay or moduli or something else, what's interesting about it is the minimal mass is set by the horizon size at the onset of the matter phase, but the maximal mass basically depends on whatever the mass of the field that's driving this matter phase is, and then also on the tilt of the power spectrum that you have to assume. So if you do this from a fundamental point of view, you could argue that the mass of this field should be in the TeV range. So that's not really a free parameter. What is a free parameter is the tilt of this power spectrum. So if you do that, let's say that you assume that the mass of the field is around the scale of, let's say, mini-split supersymmetry or whatever you like. But let's say in the TeV range, you have to restrict the power spectrum index to be less than around 1.6, otherwise you're in trouble. But what's kind of neat about it is you get out the mass of the black holes that's around 30 solar masses. You can take these numbers and change them as much as you want, but the point is that there's a cutoff in the mass of the black holes, and I'm hoping on some level this links into the last talk, because you can't get arbitrarily large black holes out of this scenario. Now, I think there'll be a talk later, maybe, that's addressing this, but if you put in different masses and different power spectra for this, there are a lot of constraints. But I think Stefano will also point out that, for example, this constraint and that constraint and that constraint are all disappearing because they're wrong. And I don't want to scoop his talk, so I'll just point to make sure you listen to that. But these lines represent different values for different masses of these candidates. And so if you put those in, this is the ratio of how much of the dark matter could be in primordial black holes versus the mass of a black hole. And what's curious about this, and it's just curious, is the idea that basically the horizon size at the time of BBN points towards 10 to 100 solar mass black holes. And that's just, maybe it's just curious, maybe it's, maybe it's silly. Anyway, so let me wrap up. So in conclusion, the main points I wanted to make is if we detect these primordial gravitational waves, this will give us a new scale of physics associated with inflation. The ineffective constraints will allow us to put constraints on whatever light particles might be around at the time of CMB or BBN. Dark matter could be made up of many sources, so we could have primordial black holes, axions, WIMPs, and again, even if you still like neutralinos or winos, like I do, they could be a small portion of what dark matter is, so it's not completely ruled out. The uncertainties in the expansion history can be interesting, and they can have implications. And most importantly, reheating from inflation to the standard model seems like a serious challenge that needs a lot of people to work on. And I'll stop there.
Thank you, Scott, for that interesting talk. We have maybe 1 or 2 minutes for questions, and I already see a question in the chat Q&A box from Alexis Plasencia, who's asked, thanks for the talk. Do you know if CMB-S4 is already fully funded? What is the timeline for the sensitivity to delta and effective that you mentioned in slide 5?
Well, so it's supported by DOE, NSF, and NASA. But given the current situation, it's not clear to me how things are going, but I think it's near term. So I think it's moving along.
Okay. I go to the next question by Sugata Ganguly, who asks, how one can detect the co-decaying dark matter?
Well, so for the sake of time, I didn't put up a plot, but indirect detection, because these things cluster, indirect detection actually puts pretty strong constraints on the scenario, depending on the parameter space. So there's enhanced annihilations in indirect detection category. So, and I don't think I have a plot for that, but maybe I do. Let me see. Yeah, okay, here. Am I still sharing the screen?
Yes.
Okay, so here's a plot of let's say you choose some decay constant versus the mass. So these lines, these are actually indirect detection constraints that Kuflik and Dror et al. Put on there. So, and then you have a unitarity bound at high mass. And then you also, if the idea was not to be in thermal equilibrium with the standard model. So that rules this region out. So and then BBN is down here at the bottom because you want to decay before that.